recap to everything that we did so far. So Smitha, we started. I mean, remember in inorganic chemistry, this is the only thing. Okay, that's transition metals, and after that, there's going to be organic. That's it. So D block elements are these elements over here. They're not all transition metals. D block elements are elements that where the last electron goes into a D subshell. So that is what is meant by D block. What is a transition metal? I told you by definition, it is something. It's a d block element that forms stable ions with incomplete d subshell. So the ions have to have an incomplete d subshell. So for example, if Fe forms a stable ion, which is Fe2 plus Fe3 plus, then its one second, then its electronic configuration ends at 3d6. So it's got an incomplete d subshell. So that means Fe can be classified as a transition metal by definition. So so Fe is a transition metal. Uh, So these are all the common oxidation state of most of the period four transition metals. A lot of them have plus two. That's their common oxidation states. They can go all the way up till plus seven. So some of them are not transition metals because zinc, for example, if it forms an ion, though it has a complete d subshell, so it's not a transition metal. Scandium, if it forms an ion, it doesn't even have a d subshell. So remember, transition metals are the ones which have incomplete d subshell. Okay, if they don't have incomplete d subshell in their in as when they form an ion, then that's not a transition metal. This is very important because that's the reason why they are colored. So if they don't have a d subshell, or if they have a completely full d subshell, then they're not going to be colored. And I'm going to explain the reason for that later on. So we last in the last class, TK, we discussed variable oxidation states, high densities, high melting boiling points, and good catalysts, right? Good catalyst, we've already done that before. Uh, so the first thing was that they had metallic bonds. TK, they were all metals. Why did they have strong metallic bonds? Because transition metals were able to. The first thing they had a smaller ionic radius. Uh, why do they have a smaller ionic radius? Because they've got more protons. So there's more attraction for electrons, for outer electrons, which is why the ion size is smaller. And the second reason is that there are going to be more delocalized electrons because in the case of iron, I told you that the 3d and 4s have very, very little energy gap, which is why यहाँ पे I've shown this over here. The 3d and 4s energy gap is very, very little, which is why electrons can not only be delocalized from the outer shell, but they can also be delocalized from the inner 3d subshell as well. Uh, the energy gap is very, very little. Why do they have higher densities? Uh, because they've got greater mass. So they're smaller, they're closer together, they're more tightly packed. They've got more delocalized electrons, which leads to stronger metallic bonds. And the density is high because they've got more mass compared to other metals. So, and they're more packed as well. TK, we did all of that. And we started off on this thing. TK, we started off on colored complexes. This is what we started. And I told you that this colored complexes thing and the complex thing, that's the main topic, basically. I said last one, the last part. Was that all clear? Is that clear? I guess we can start with colored
Yes,
copy.
sir.
So, uh,
Sir,
yeah,
I think there is a student who wants to enter, like we just got a message.
just one second. Yeah. ठीक है. I said now colored complexes. ठीक है, we're gonna start with colored complexes. Just one second. I said colored complexes is what's a complex? I told you. I briefly told you that we started off with copper sulfate, and I told you that it's aqueous. So we've learned that when copper sulfate is aqueous, it dissociates and forms two ions. One is copper 2 plus, and the other one is SO4 minus 2, right? So you've got these two ions that are formed in solution. Now, the thing with these ions is that these ions are not as simple as they look. For example, if copper 2 plus is floating in water, So it's not floating alone in water. What happens is water is a highly polar compound. It's a very polar compound. It's got a lot of lone pairs. It's got a lot of negative charge on those lone pairs. So what happens is the negative electrons they get attracted to the copper 2 plus and they natively bond to it. Okay, so this thing over here, this bond over here, that's a okay, let me write this down. This bond over here is our dative bond or a coordinate bond. So it's a dative bond. The lone pairs of water get attracted to the copper 2 plus. But not only would one water molecule get attracted to it, it's going to be surrounded by water molecules from all sides. There's going to be water molecules getting attracted to it from all six sides. And so from all six sides, it's going to, again, let me take one of the dotted means that it's going, just a second. Yeah. So the dotted indicates that it's going behind. These are all six axes. Okay, it's an octahedral complex. The angles are 90 degrees. The way you're going to write this complex is it's going to be copper surrounded by six water molecules and having a +2 charge. The overall charge would be +2 because copper is +2 and the water molecule is neutral. So all the water molecules that are sticking to the copper 2 plus in the middle, um, the overall charge would therefore be +2. And this one is called a hexa aqua copper 2 complex. Aqua just means water, surrounded by water. Hexa means six water molecules. I told you this thing is going to be called a ligand. It's a species with lone pairs of electrons and natively bonds to the metal cations, forming a complex ion. And we wrote down a definition. We wrote down the definition for complex ions, which was that it's an ion formed when a central metal cation natively bonds to ligands. So that's what a complex ion is. Both definitions are very important because they're going to ask for that. Okay. So moving on, this is what we did yesterday. So complex ion, is that clear? Do you get clear?
Yes, sir.
So now,
Sir, so like on only yesterday you guys on Saturday only you guys started transition
yeah,
metals or on
is that
Friday?
Saturday?
Okay. Okay.
ठीक है और ये ना I think this one I've sent you the link. It's this is I think this is the 2 November lecture. I've uploaded it. ठीक है?
You have it on your notebook, yeah?
Yeah,
Okay.
I've sent you the drive link as well. I said now colored complexes. So that's the first one. It's what was the color of this complex? It's blue colored, right? This is the blue solution that you're going to see when you see copper 2 plus ions in water. Okay, that's what this is. And I'll just I'll just post a picture because the colors are very important because they're going to ask you. I mean, you pretty much know what the colors are. ठीक है बस इसको just one second let me quickly. ठीक है so that's the blue colored solution. That's copper hexa aqua copper 2 complex. So the thing you know as copper sulfate, that's this thing. So now the next thing that's going to happen is what if I start adding another ligand to it or another. So what if I start adding ammonia to it? Now remember, ammonia is also a ligand. So that's being added. Now, what's going to happen to my complex is that there's going to be ligand exchange that's going to take place. I'm going to copy the whole thing. Okay, that used to be my blue solution. So there's ammonia being added because that's a complex, the old one. Used to be a blue solution. Now, what ammonia would do is it's going to knock out some of the water molecules. And in its place, ammonia will start since you're adding ammonia. Now, ammonia is trigonal pyramidal and it's NH3 and it's got a lone pair as well. And it's got a very negative lone pair as well, just like water. So some of the water molecules are going to get knocked out by the ammonia that you're adding. So it could be one, it could be all six of them could be knocked out as well. So I'm just going to knock out a few of them. I said, do you know from O levels what happens when ammonia gets added to copper sulfate aqueous? Like what is the color change? Any idea?
Dark
It's a
blue.
need deep blue solution. It forms. So what's happening is that let's assume that two of the water molecules get knocked out. So you're left with two NH3s and there are four water molecules left, and there are two NH3 now part of the complex, right? So this one. So this one is going to be your deep blue solution. Okay, that one is going to be your deep blue solution, and it could be any number of so make sure that any it depends on how much ammonia you're adding. Any number of ammonia ligands can get attached, replacing the water molecules. So it's a variable number. So for example, you could I mean the same formula you could see this thing. It's you could see copper with in total there's going to be six. So you could have five NH3s and you could have one water molecule. The overall charge is still plus two. Or you could also have all six of them could be NH3. So it depends, it's your choice. You can write any one of them. Okay? The only idea is that the water molecules are getting knocked out while while you're adding ammonia to it. And as you're adding ammonia to it, um, the color becomes deep blue. Now it's very, very dark in color. Okay, is this clear?
Yes.
Okay, so I'm going to show you what's going to happen that this was a test for. So you can see, I guess you can see over here that the color is slowly changing. Look at color there. So the color is changing into very, very dark, into a very dark color. Okay, so the same blue solution now becomes very deep blue. So the colors, one thing you'll get an idea is that the color of the complex depends a lot on the ligand that's getting attached. Okay, so we're going to explain why they're colored in the first place, but after we study all these complexes. I said then the next one, you could add NaOH to it as well. And remember, this reaction is known as ligand exchange. The type of reaction, okay, that's called ligand exchange. One ligand getting exchanged by another ligand. I said now the other thing that could happen is that you could add NaOH to it. Okay, so you can add NaOH aqueous to it. Now, so when you add NaOH aqueous to it, pretty much the same thing happens. But the idea is you can add NaOH to any one of them. Now, kind of the same thing happens. I'm going to pick water molecule because our starting point is copper sulfate aqueous, so let's pick copper sulfate aqueous. Okay, now what happens is what ligand is present in NaOH aqueous? उसमें जो ligand है ना, that's OH minus one. So now what will happen is that your water molecules are going to get knocked out by they're going to get knocked out by OH ions. So you're going to start seeing OH minus one bringing its lone pairs into this octahedral complex. ठीक है? Is this clear?
Yes, sir. And sir, what happens to the sodium, like Na positive?
नहीं, that's just a
It just stays
spectator.
in the solution?
नहीं, that's just a spectator
Okay.
ion. ठीक है? So I'm going to write
Okay, sir.
I'm going to write OH minus one ligand, right? So I'm adding NaOH aqueous. I said now what happens is now the problem with this one is that only two of the OH ions get attached to it, not more than two. In the previous case, you could have any number of ammonia coming in, right? Can anyone just guess why would there be just two OH ions getting attached to it? Any idea?
Sir, because two negative ions and like positive and negative charge will be balanced. That's why.
Okay, so what's the charge now on the whole thing? It's zero, right? You got no charge, right? Because the charges have been balanced out. So after it becomes neutral, it stops attracting OH ions. So which is why in the previous case the charge wasn't getting neutral. It was, I mean, you had plus two, and no matter how many ammonia molecules, because ammonia is neutral, right? So no matter how many ammonia molecules get attached to it, the charge would simply not change. ठीक है? Because copper was plus two and ammonia was neutral. So in that case, the charges they never changed, and so which is why it was always plus two, which is why it was still attracting ligands, right? But now once it becomes neutral, it no longer attracts ligands. Is that clear? So so the complex that you have now is it's CuOH twice, and there are four water molecules, right? And it's completely neutral now. Acha, since it's neutral, would it attract the water molecules even? Would it attract water molecules or would it not attract water molecules? क्या होगा इस Afan, would it attract water molecules or not?
No, sir. Charge zero है.
ठीक है, so OH minus one is kind of neutralizing the charge. So after this, there's no further attraction for water molecules even. So all these water molecules they drop off because they're not going to be attracted to something that almost has zero charge. So it's just copper with OH ions, and it no longer has any charge, so it no longer attracts water molecules even. So this thing would eventually turn into a precipitate of CuOH2. It's going to form an ionic compound, a solid ionic, and it's an insoluble ionic lattice. So a solid precipitate would form, and the water molecules would even leave the complex, right? So it would no longer be a complex. So it's going to be a pale blue precipitate. ठीक है? Is this clear?
Yes.
Yes, sir.
अच्छा, now same. So we and this is not a ligand exchange reaction. Remember that. ठीक है? This one over here, because it was a ligand exchange, but it turned into a precipitation reaction where you had an ionic precipitate getting formed. So this one is a simple precipitation. So basically, you had a complex, but the OH ions they took the copper out of the complex, and they eventually formed a pale blue precipitate. Uh, clear as Amna, is this clear, Zaina? Zuhair, is this clear?
Yes.
Yes.
ठीक है?
Yes, sir.
अच्छा, and the reason I'm drawing all these diagrams is because they're going to ask you to draw all these diagrams. Diagrams are very important. ठीक है? The whole complex thing. And then the third one. The third one is what if I add concentrated HCl? ठीक है? Remember, this is going to be very concentrated HCl. So concentrated HCl has this ligand. It's got Cl minus one ligand. Now the thing with Cl minus one is that it's a lot bigger in size. Remember, Cl has three shells. It's got 18 electrons. Uh, the MR is or the AR relative atomic mass of Cl minus one is 35.5, right? So it's much bigger in size compared to OH ion. So OH ion, the molecular mass is or the ionic mass, formula mass is 16 plus 1, that's 17, right? Water is 18. So this is like twice as big. So the thing with Cl minus 1 is it because the Cl ion is bigger in size, you can't fit a lot of them around it, right? So what happens is Cl minus 1 does not form an octahedral complex. It instead forms a tetrahedral complex. So when you have copper 2 plus and the water molecules are getting knocked out by the Cl ion, the thing with Cl ions is that not a lot of them will get attracted to it. So let's say there's one Cl ion over here with its lone pairs, and there's going to be, I'm going to draw a tetrahedral arrangement. So only four Cl ions can fit around because you're running out of space. Then you're going to have the wedge-shaped bond. Just a second. And then there's going to be one dotted. So there would be four Cl ions getting attached to it. And this one is not going to form a precipitate because copper chloride happens to be very soluble. So it dissolves into the HCl back again. And the copper ions are floating around in Cl ions. So it generally gets, the overall charge is going to be -2. Okay, so it will eventually get surrounded by, because it's not forming a precipitate. It's not forming an ionic compound. The precipitate dissolves very quickly back into copper chloride is very, very soluble. So which is why it's just copper ions floating around in water. It doesn't form the ionic solid. And so this complex is Cu, Cl4, 2 minus. Okay, that's your complex. And this one has a yellowish green color. So this one has a yellowish green color. Uh, that's it. Okay, so those are my four. Uh, and this is also ligand exchange, this one. Okay, is this thing clear that you've got bigger ligands, you can't fit a lot of them around it? So which is why
Yes.
you get tetrahedral complexes in this case. Okay, remember the shapes of the complexes, it all depends on the ratio of the ions, like what size are the ions. So you can get all types of shapes. You can get trigonal, planar, but the ones that we want to study are these ones. Okay, these are the important ones. So we need to study all of these. So we started off with copper with water, and we got these three complexes. And you can switch between these complexes as well. You can go from this complex to this complex by adding Cl ions. It's pretty obvious. You add Cl ions, concentrate HCl. So the copper ion would get surrounded by Cl ions. You can go from here to here. You can bring in the OH ions, add NaOH to this. So you can sort of interchange between them as well. Okay, is this clear? All of this.
Yes.
Yes, sir.
So the same thing, exact same scenario, exact same complexes. Cobalt is going to have exactly the same complexes. So I'm not going to draw all of this for cobalt. The only difference between cobalt and these ones is that the colors would be different. So it's going to have exactly the same complexes as Cu2 plus, except all the colors would be different. So starting with the first one, cobalt with water, that's so when you add water to cobalt, it's pink in color. Then you have cobalt with ammonia. Yeah, that's 2 plus, that's brown in color. Then you have cobalt with Cl. Okay, even the formulas are exactly the same. This one is what is the color for this one? This one is blue in color. And then finally you have copper with copper hydroxide precipitate. That's a pale blue precipitate. Okay, so it's exactly the same except that the colors are different. That's it. Okay, is this clear?
Yes, sir. And sir, if we have like cobalt and ammonia like six, or we have four, so the color will
No,
remain brown.
no, that would pretty much be the same.
Okay, sir.
Okay. So next thing is we have to write equations for all of these reactions. Okay, so you should learn how to, and these are a lot of them are reversible reactions. So make sure note that Ligan exchange reactions are reversible. So you go from one to the other and you can come back again. For example, if I add water molecules back again, the Cl ligands would get substituted by water back again. So they're all reversible reactions. So starting with the first equation. Um, so they're going to write something like this that, for example, they take copper sulfate aqueous. What you do is you add ammonia. Okay, let's start with NaOH. You add few drops of NaOH, and what you get is you get a pale blue precipitate formed. And so then you add excess NaOH. So the result is pale blue precipitate does not dissolve or is insoluble. So you're going to be asked to explain this. Using an equation basically, all you have to do is you have to write an equation for this. So what's happening is that you had copper. So there's only one equation, copper with 6 water molecules. Okay, copper sulfate aqueous is this thing. And you added OH to it, two of them. And there was a reversible reaction where the copper ended up forming a pale blue precipitate and the 6 water molecules they got knocked out. So this is aqueous. Okay, that's your. So the same thing in equation form, Tiki, and they're going to ask you exactly. I said, remember, there's not much of a variety of questions on this. They're going to ask you exactly the same thing. Okay, they're just going to ask you to write the equations. Uh, the next one. The next one is again you've got copper sulfate aqueous. So you add this one is slightly more complicated. You add few drops of ammonia, and what happens is you get a pale blue precipitate forms. And then you add excess ammonia. So what happens? Pale blue precipitate dissolves. And what does it do? It gives a deep blue solution. So you have to explain this. Now, the first thing that happens is when you're trying to explain this is initially ammonia does not behave as a ligand. Initially, what happens is the ammonia behaves as a base. The ammonia reacts with water. When you add a few drops, the ammonia reacts with water, and when it reacts with water, it accepts the H+1 from the water and it ends up producing OH ions. So start when it actually ends up forming OH ions. So what you get at the start is the pale blue precipitate. You get the same reaction as above. So hence, I mean exactly the same reaction. Okay, so you get exactly so right at the beginning, you get exactly the same reaction. The OH ions form the insoluble. Okay, so is this clear that initially you're getting a pale blue precipitate? Why are you getting a pale blue precipitate? Because the ammonia is actually producing OH ions and you get the same COH2 precipitate. Okay, is this clear?
Yes, sir.
And after that, what happens is when you add ammonia in excess, then what happens is it behaves as a ligand. So what it's going to do is it's going to take the copper hydroxide and ligand exchange would start happening. So the COH2, which was a solid blue precipitate, pale blue, the ammonia molecules will start, and since it's aqueous, so let's add in some water molecules as well. TK, it's your choice. TK, remember I told you with ammonia, it's your choice how many ammonia and how many water molecules you're going to add. So the copper would then eventually get surrounded by ammonia ligands, four of them, and let's say two water molecules. And the whole thing will have a +2 charge, and that's your deep blue solution. And what's going to get knocked out? The OH ions are going to get knocked out. Okay, so this is aqueous ammonia, liquid water that's getting added. So you're getting aqueous complex of copper with ammonia and OH ions that's also aqueous. Over here, remember over here you can go with any number of NH3s. You can have all six of them to be NH3s as well. Now this is your deep blue solution. ठीक है? Is this clear? This thing clear है सारों को? Is this clear? Zaira, is this clear? Akshita, is this clear? Amna, Afan, clear है? Maheen?
Yes.
Ji, sir, clear.
Okay, so remember this is, and remember you have to just remember all of this. Okay, they're going to ask you exactly the same thing. Okay. The last one, if you add concentrated HCl to, that's an easy one. If you add concentrate, we just did that. Okay, we just have to write an equation for that. So again, you've got copper sulfate aqueous. And what do? We add concentrated HCl. What happens? You get a yellow, greenish yellow solution. So what's the reason? What's the explanation for this? So it's simple that it's copper with six water molecules having a +2 charge. And um, what am I adding? It's so four Cl ions would come in. Cl is the bigger. You remember to have a reversible sign. So it's going to form CuCl4, 2 minus, and the water are going to get knocked out. Six water molecules getting knocked out. Because this is aqueous. And this one is going to be liquid. And the CuCl4 is in reality is actually yellow in color. And this in reality is blue in color. The thing is that the reason you see greenish yellow is that blue and yellow they mix up and they form a greenish yellow solution. So normally you never get a yellow solution because the yellow has some blue mixed into it. There's some CuH2O6 that's left because it's a reversible reaction, which is why it's never really you never really see yellow. It's something having a shade of green. Okay, so that's all your Ligan exchange reaction. Okay, and remember you're going to have the same exact equations, exact equations for cobalt. Okay, so you're going to do exactly the same for cobalt. Okay, is this clear?
Yes, sir.
So now I'm just okay, we're running out of time. Okay, so we'll continue the next thing. We're done with this. Okay, we're done with the equations. You have to remember them exactly the way they are, and they're going to ask you exactly the same explanation to show all of this using an equation. All of these things, draw these complexes. You should know the colors of these complexes. Okay. So we'll continue in the next class. We'll probably discuss why they're colored. Okay.
So, sir,
Okay, sir.
like they
Allah
will
Hafiz.
only ask us about copper and cobalt and no other thing. मतलब कोई भी चीज आ
हाँ,
सकती
that's
है
नहीं, it's
इनके
copper
अलावा
and cobalt only.
Okay.
They can ask you about other stuff, but you're going to apply the same reasoning and the same logic and the same equations and the same.
But
मतलब they
sir,
are,
what about the colors? Like हमें color भी उनको
then
याद
they
करना
नहीं,
होगा.
then they're going to give you colors. ठीक है,
Okay.
there was one question on nickel, but they were using the same terms and you had to use the same equations. I mean, for example, they told us that there was some blue nickel solution and they added ammonia to it and it turned into a gray solution. So you had to write the same reaction. ठीक है, is that clear?
Okay, sir. Yes, sir.
Okay, everyone. Take care
Allah Hafiz, sir.
of this.